Okay, so now we are going to talk about the dot product between two vectors. The idea is that the dot product is a new operation which is slightly different from the operations we have seen before about like adding vectors or multiplying a vector by a number. And what you do with the dot product is somehow measure how much the vectors interact. So what's the key idea? So with the dot product, you should think of it as measuring the interaction between two vectors. Okay. So what I mean by that is that what we will do with the dot product is that we'll take two vectors, say u and v, and what we will do is we will take the dot product between them which is denoted u dot v, hence the name. Okay, so this quantity, this expression will denote the dot product between two vectors. Notice that it's a similar notation to the ordinary notation for multiplication of numbers or scalars. Okay, and so what you should think of this is that given two vectors, this operation will give you a single number. So it will give you just a number. Remember a synonym in this course for numbers is scalar, more or less. So out of two vectors you get a number, and the point morally what you should think about this dot product giving you is that again if the dot product is 0, then in a way the vectors, you should regard them as being like independent of each other. Okay, and so in order to tell you more precisely what the dot product is, let me just say a bit more about what the norm or magnitude of a vector is supposed to be. So let's talk about that for a second. So as I have said before, a vector is specified by its size and a direction in space, so that when you talk about the magnitude or the norm of a vector, what you're recording is the size of the vector. So this is the size of a vector, and say, so if your vector and if your vector is v, if this arrow is v, then this notation means the size or length of this vector. So for example, if the length of this arrow is 3, then you would say that the norm of V is 3, and you would write something like this. So again, like the notation is supposed to suggest something like an absolute value, because if you think of the absolute value of a number, say the absolute value of 3 is 3, but the absolute value of -3 is 3, because you just care about like the actual size of that number relative to the origin, if you think of them as being on the real line. And so this sort of conveys the same notion that you just care about like the size and not like how it is pointing. So what that means is that you could have this vector, this vector, this vector, let's call v1, v2, v3, and well, suppose that I'm drawing them so that they're actually of the same size, and so it's perfectly fine to have 3 different vectors with the same size, right? So same size or norm, but they're still different vectors. So the norm just records one piece of the information of what makes a vector. And why is this useful? Because as I was saying, I want to tell you a formula for the dot product. Okay, and so what's the idea? Let me not erase this. Let's leave it. Let's leave that here, and I'll refer to it in a second. But so what's the point of the dot product? Well, so in order to compute the dot product, what you will do, as I have said before, you are free to move vectors around. And you will move them so that they start from the same place, the same point in space, and then there's going to be some angle between them, right? So strictly speaking, if you think of these, there are always 2 angles you could choose from, right? You could choose this one, or you could choose this other angle, right? Well, both of them add up to 360 degrees. So one of them is always less than 180 degrees, or it could be 180 degrees. So you always choose the angle that's smallest. Okay, another tiny technical glitch, but not too much to worry about. So if you have 2 vectors, u and v, let's see, let me use this color. There's some angle between them. You always choose the angle which is between 0 and 180 degrees. And then the key formula of the dot product that you need to remember is that u dot v is, as I said before, going to be a number, and this number will compute in the following way. So we take the norm of u, which is again just the size of the vector. We multiply it with the size of the vector v, and then times the cosine of the angle between them. Okay, so that's the formula for the dot product. Which you need to know. Now, just based on this formula, there are some consequences that you can draw. So what's the most, some examples or properties? Well, the first example is what happens when these two vectors are at an angle of 90 degrees. Well, so as you can see here, right, that means that the vectors are perpendicular. So they're perpendicular. Another way to say this is that they are, which is like a more technical terminology that sometimes is used in more advanced courses, is that they are orthogonal to each other. So another name for this is like orthogonal vectors. And if you follow the recipe for the dot product in this case, what's the dot product supposed to be here? Well, in this case, the u dot v, again, is the norm of u times the norm of v times, let me just emphasize the important feature here, which is that you're using the cosine of pi over 2. But hopefully you remember that cosine of pi over 2 is just 0. And so you're whatever this number is, we don't care about because it's being multiplied against 0. And so that just tells you the dot product is 0. And so in fact, it happens to be the case that two vectors, so what we found here is that the dot product between two vectors is 0. This is the same as the two vectors making an angle being perpendicular to each other. Okay? So I had said before that you should think of two vectors having a dot product 0 as being independent of each other. And the perspective to have here is that the reason why you think of these two vectors as being independent is that somehow there's no shadow, right? Imagine that you have like a light bulb. You try to see like the shadow that one vector makes along the other. If they're perpendicular, the shadow like collapses to a point, right? Like if you had, we will explore this later when we talk about orthogonal projections. But if you have two vectors which are not at a 90-degree angle, then you can sort of think of what's the shadow that this vector makes along this other vector, and there's a non-trivial shadow, right, because the angle is not 90. But when the angle is 90, somehow the shadow collapses to a point, and so that's why we think of them as being independent. Okay? The other case, which is useful to keep in mind, is what happens when the vectors are the same So when the vectors are the same, the angle will be 0, and now the previous recording should be fine, so I'll let you keep watching that one. The dot product of a vector with itself, if you follow this formula, will be the norm of u times the norm of u times cosine of the angle, which is 0. And so that just gives you cosine of 0 is 1. So you get the norm of u squared. And so you also, from here, find a very useful formula, okay, which is that, right, so what this is saying is that if you take square roots on both sides, this is giving you the result that the size of a vector is really the square root of the dot product of that vector with itself. And that actually okay, so what this is saying is that you can use dot product to find the norm of a vector. And this will be very useful. So for example, when you think of the vector as being the velocity of a particle, then the norm of the velocity will be the dot product of the velocity with itself, and so or the square root of that, and that's going to be related to the speed of the particle. Okay? And here, and we'll see again that this can be used in ways you would not expect to compute the norm. But let me just maybe say this, what happens here, and another property. So now I'm taking the vector and minus the vector, right? So again, their sizes are the same. It's just that now the cosine of you get the you would put, like, say cosine of pi, and so in the end if you use this formula, right, you find that the dot product of u with negative u is minus the norm squared. Okay, and this formula on its own is not that interesting. It's just to bring out the point that the dot product of two vectors can be negative. So it's also, so what this is saying is that the dot product, so in general, the dot product can be 0, positive, or negative. Again, the really useful case is when it's 0, in which case that's the same as saying that the vectors are perpendicular. As I mentioned before, like, we want to think of perpendicular vectors as being independent of each other. So actually, like, sometimes in statistics, like, you can represent some data with a vector, which means that in this case, you would say, like, if you think of vectors as some sort of variables or carrying some statistical data, you would say that the vectors are uncorrelated. And here, when the dot product is positive, again, that means that there's some sort of, like, common information among themselves, and if you wanted to use, like, some statistical terminology, you would say that they're positively correlated. And as you might imagine here, that if they happen to give you a negative answer, you would say that there's like a negative correlation between them. Okay? One thing that may be useful to point out right now, as you can see from the formula, another key property of the dot product, which should not come as a surprise, is that, well, multiplying the size of u times the size of v is the same as multiplying the size of v times the size of u. So what I'm trying to say is that the dot product between u and v is the same as the dot product between v and u. And so what that means is that you can sort of move around the order of the factors in the dot product without having to worry too much about it. But yeah, let me just maybe finish with this. Something like say something like this. So take two vectors, take their dot product, and then take a third vector. An expression like this does not make sense because really this is when you take the dot product between two vectors, you already get a number. So you cannot take the dot product between a number and a vector. You can just multiply them in that ordinary way, as we learned before, of a scalar times a vector, but not as in the sense of making the dot product between the vector and a number, right? So dot product is only defined when so dot product is between two vectors always. Okay? So what I will do, again, I haven't done any examples. I'll do in the next video some examples. The pattern that I'm doing is like, first I'll tell you like the geometric way to think about these operations, and then I'll tell you the way in which in practice you actually compute them. Okay? So next time I'll tell you how to actually compute the dot product between two vectors and what are other conclusions you can extract from it.